so nicely in this workshop. So it's really, really, it's absolute waste to not be able to really effectively campus. So that's my segue to John. My colleague John Shea, who's a professor here in my department of electrical engineering. He's a graduate from Clemson back in '98, and he received a lifetime award for technical achievement at Milcom, IEEE Milcom, in 2012. And it says here, I don't know if it's true, the only two-time winner of the Fred Ellickson Award for the best paper in the unclassified program of Milcom. So you can see the papers here exists. And his interests are in wireless communication, networking, emphasis on military communications, networked autonomous systems, physical layer security, and cross-layer design. And we're going to hear about biological systems.
That's right. I don't have anything to say about biological systems, unfortunately, but that's right. This is my biological system. I always thought that you should, brand yourself in some way. Like, so this every talk, I make my students put this thing on their talk, and then you'll know if you see an alligator, that's my student. So, but I do want to thank some of my collaborators on this stuff. So I'll be talking just a little bit about control stuff and how some communication and networking and things like that fit in with control things. And so one of my big collaborators on that is another professor here at Warren-Dixon from Mechanical and Aerospace Engineering, and my postdoc and former PhD student, my current PhD student, Jishin, who I was chasing to give me fresh graphs for the talk, so 11:30 this morning, so keeping in the spirit of academic doing things the last minute. And my sponsors for this work are NSF and the AFRL, Mathematical and Optimization Institute. So I'm going to talk about basically two things that I think are maybe interesting and related to things you guys are talking about. I'm sorry I missed this morning's talk. I had other commitments that I just couldn't get out of, but I think there's some, looking at the titles, some things that are related to things I'll be talking about, so hopefully it'll fit nicely together. One of the things that we're interested in is we're interested in systems of autonomous vehicles, and we're interested in how can you coordinate their movement, for different purposes, how can you coordinate their movement to achieve certain goals, or we're going to talk about how I can use them to attack a network, how we can use them to defend a network. These are all the sorts of things that we're interested in. But one of our first problems is thinking about, well, what if I have some system of vehicles and I just want to reconfigure it? But while I do the reconfiguration, if these are sort of dumb quadcopters that can't do a lot, maybe I need to have continuous control of those, and I need my network to be connected during however I want to move it. And so here I have just a few quadcopters, but we're thinking big systems with tens or hundreds of vehicles in it. And we start by attacking this problem where we have some vehicles. The vehicles are homogeneous in the sense that they are all identical. So if I want to move them to some other place, I don't care which one goes to a different place. I just want to look at, all right, I have this shape of the system, and I want to make this shape into something else. Then how should I do that? Like a few different things. Like, how do I decide which one goes to which position? Then how do I actually do that movement? And so we kind of decompose the problem. Not saying that this isn't some sort of optimal decomposition, but just a practical decomposition. That we need the mapping. Which vehicles in some initial formation go to the desired position, which I'll call roles in the final formation. And then how do we actually implement the control algorithm that are going to move those into the specified formation, but have this constraint that network connectivity can never be lost. So, we try and relax these things in some of our later work, but this is where we started. And so one of the things we're going to do here is use an analogy to routing in networks to actually move these vehicles through the network or through the formation in such a way that I can always preserve the connectivity. And I'll show you that through some examples. What's that?
What are the impediments to connectivity?
So here, this is the simplest case, that you just have basically a protocol model. You have a certain range that you can communicate as long as you stay within that range, right? So free space or exponential path loss would fit with that, but any protocol model. So no fading or anything like that, because then you can't guarantee anything, right? So if we take our initial network topology and reduce it to a tree, then we can move the vehicles along the tree using a prefix routing type of technique. So I treat the vehicles as if they're packets. I've pushed them through the tree. If I only move the vehicles that are at a leaf at each step, then I'm guaranteed to never break connectivity. And so I'll show you how that works. But one of the things we need to do is we need to figure out, well, how do I determine what tree topology in that initial network that I would work with? And so one of the things we're doing here is we're taking a problem that is a coupled problem between the formation, which is physical, and the network topology, which is sort of determined by that physical formation. And then we work across these two layers a little bit. So to optimize the initial tree topology, then we start, just choose some spanning tree from the final network, and then we want to choose a mapping phi in such a way that we're going to minimize the number of edges that the vehicles have to traverse when we transition from the initial tree topology to the final tree topology. So if this is the, here's the number of hops, the distance from the number of hops. I'm going from some initial network to some final network. For each node u, where I go to, it gets mapped to some position phi of u, and then what I want to determine is, for all phis, then and starting graphs, then what's the best phi? What's the best way to determine this mapping? And the way we do that is to solve a graph matching problem. We use a subgraph matching because we can't guarantee that these things are going to align with each other in any way. If they happen to be that the initial subgraph and the final desired final tree are isomorphic, then there's an algorithm called Ullmann's algorithm. It has very high complexity, but it will give you the actual mapping if they're isomorphic. If not, then we have to use some form of approximate subgraph matching, and we use what's called Umiyama's method. Basically, we set up some cost function that's going to tell us what's the cost for different types of ways in which we're not matching properly, and I'll show you kind of how that goes. So we have a weight associated with the input graph and weights associated with the final graph with the mapped edges from phi. And what we want to do in our cost function is to make it so that if your mapping is going to cause you to move a lot, then your cost should be higher, basically. And the way we do that is that we assign more weighting to those edges that are closer to the root, and I'm sorry, more error, more weighting to the edges that are further from the root, because those are the ones that are more likely, if you miss them, to cost you a lot to recover them. And so basically this problem then, when you can be reformulated in this problem in this form here, so the costs can be written in terms of a permutation matrix that looks something like this, and then if we do spectral decomposition on the adjacency matrices of the input and the desired final graphs, then relax the domain of the permutation matrix, then we can, instead of solving this combinatorial optimization problem, then we can relax it and solve it over the real domain. In the case that the initial and final graphs are isomorphic, then we can show that we just need to solve for this S matrix, which then can be guaranteed to make P hat a permutation matrix, and this actually gives the exact solution. Then we can reduce the problem in that case to just solving this trace type of thing. So find the permutation matrix that maximizes this trace, and that permutation matrix can be solved by Hungarian algorithm. So that it's pretty straightforward. But the thing is, okay, if the graphs are isomorphic, it works really well. If they're not isomorphic, then the solutions are not necessarily great. You can take them and then you can improve them via something like some meta-heuristic technique. We look somewhat at that. But you do all that work, which, so the complexity is not bad here because we just have to do the spectral decomposition and then Hungarian algorithm. So we're pretty much bounded in complexity by the doing the eigen decomposition. But then after we do the subgraph matching, we need a tree, and because it's matching up subgraphs, it will not necessarily result in a tree. So there'll be edges in one graph that just don't exist in the other graph. It's an approximate matching. And so after we do our matching, then we have to build our initial tree topology. And what we do is we start at the root node and then kind of work our way down to to build an initial tree, and I'll just show that by example rather than talking too much about it. And the idea will be, well, whenever the two graphs match, so whenever there are edges that are in both the initial topology and the final topology, then I'll preserve those, but when they're missing, then I'll add in the best one I can to sort of minimize the amount of travel that my nodes will have to do. So to fill in the missing nodes, then basically, like I said, we're minimizing the distance that a node will have to move from its position in the final graph to its mapped position in the initial graph. So its starting position to where we're going to need to move it. And so nodes that are in the initial graph but that are not connected at the deepest level of the tree are then going to be connected to minimize their distance in the final tree. And I'll just kind of show you how this goes. This is an example my student put together, so I think it kind of gives the idea. So we have two graphs. So I have my initial topology, which may not be a tree topology at all. I have my final desired topology, which we've chosen to be a tree because I just took a spanning tree from whatever I wanted to achieve. And then I do subgraph matching, and it'll give me some result like this, where you can see that I'm trying to figure out what's the best way for me to align these nodes onto this, and it does a good job with 1, 2, and 5, and 1, 3, and 6, but 4 and 7 are kind of left somewhere else, right? Because there's just no other matching that can be achieved in this particular case. And then we reduce these to tree topologies, and then we start to build our initial tree. So you can see that like these nodes, although they're connected in the initial graph, when I do the mapping, these edges don't exist in the mapping. So I have to figure out to build a tree out of this, that these nodes are just disconnected after I do the subgraph matching. It doesn't guarantee you have a connected graph even. So we just start at the root and we start building edges that exist in our final topology, in our initial and final topologies. And so these edges all map up in our initial and final topologies. And then after I do that, then I have some leftover nodes here and some nodes here that I need to map. And so I just start connecting those where I can, basically. And then that's the result of the tree topology. And the whole purpose of building this tree topology is that that's going to determine how our nodes are going to move. They don't move exactly along we won't make them move exactly along the tree topology we establish. We use that tree topology in our physical formation reconfiguration algorithm, the control algorithm. And the way we do that is we set up what we call information flows. And the information flows are along two-hop sets of nodes. And so we're going to move along these two-hop routes at a time, and we're going to set up these information flows based on an idea called prefix routing. So we apply prefix labels to our tree, which is also called a tree but spelled differently, and then the labels will uniquely determine the routes that the nodes are going to flow through the network. So here's the two networks where I've just applied a prefix labeling to each of these. And so what I have once I do this prefix labeling is that some of the nodes in my initial tree are not where they belong. We call these the extra nodes. And some of the nodes are missing. So 0, 3 and 0, 3, 1 exist over here. And so I need to fill those in up here, right? And so what I do is I establish, the root will coordinate how these guys are going to move so that I always move only the leaf nodes in my tree at any given time. Once the leaf nodes know where they're going, then they establish an information flow with the two-hop neighbor to where they're going to go to. And so once they have that information flow, they will start to move in the direction of where they need to go. Now, the physical control algorithm doesn't exactly move them along these paths. They try to move them towards where they need to be, basically. And so once they move up the tree, then again, they can now, once they can connect with this node, they can establish a information flow to their next two-hop neighbor and move again. And then once this node is connected to the root, in terms of the network formation, then he's already in position 0, 3 and just needs to be relabeled. But this node needs to move until he connects with that node, so he establishes an information flow, and then once he moves close enough to communicate, then he becomes that neighbor, and then they can relabel to 0, 3 and 0, 3, 1, and they're done. Okay? And so the actual movement is via navigation function-based control, decentralized control, and so here's all the math. I'm not a control person, but you can basically see that what's happening is you have some functions here. They're going to be dependent on the positions you're trying to achieve, and then there are also some variables for preventing collision and things like this. So
the graph, so the connection graph is in some sense isomorphic with the position graph?
That's right. So the topology, the network topology is connected to the physical formation. We use the network topology to determine how we're going to move, but then the actual physical movement is controlled through physical variables. Exactly.
The point is, if I'm too removed, or so there's two spaces that we're operating in. There's routing space.
That's right.
And
it's physical space.
So they're isomorphic.
Yeah, exactly.
Can I ask two questions?
Yeah.
One is, in what sense is this decentralized?
It's decentralized in the sense that each vehicle only needs to communicate with its two-hop neighbors in order to do the movement. That there's no communication with the rest of the. That's right. Yeah, it has to communicate with whoever is within 2 hops of it, and so it has to have a flow of information that it can go not just to the people it could directly talk to, but it has to talk to its 2-hop neighbor.
This hasn't been explained yet, right?
Yeah, I mean, I didn't say much about this. I think basically these are these are positions of the 2 vehicles that you're trying to that move. This is the relative. So you want to establish a relative position that's set up by Cij. So this is your goal, sort of your goal function, and this beta I. I believe is like trying to prevent collisions. And
this VI is the function was initially linear and spot does for y. And so that's some sort of, but I was also wondering, how do you avoid collisions if you only know about your 2-hop neighbors rather than say your neighbor?
Right, yeah, you know your neighbor and your next neighbor, right? So yeah, so you know 2 hops away.
But you can be physically co-located, right?
Well, I mean, let's play that game. Go back a slide if you would.
Yeah.
So we're just hijacking the talk.
No, yeah, sorry. No problem.
So let's imagine that we have this tree, this tri-level structure, and now just extend it down about 10 levels. So you got things that are physically contiguous, and let's make it so that they are literally, that this thing is exactly isomorphic to the physical position. So network.
Yeah, and you'll see that it's not like an exact isomorphism. In fact, the physical movement will not move directly along these graphs. That you're going to move around through the graph, and I have an example that shows exactly how you physically move. How do you maintain connectivity? So one of these things is actually I believe this one is for maintaining connectivity in your navigation function. So you're moving in such a way that at all times you're guaranteeing that you're going to achieve connectivity. And that's one of the reasons that this thing kind of goes up to some value that prevents you from breaking that connectivity. What we try to do is that there's a lot of results out there that address similar problems to this, but what they require is that you always maintain the same links. You can never break a link once you establish it. And in our formulation, you can break links. Because when I move up the tree to a new position, then I establish a new information flow, and then I can break the links with anything I had before.
That's the reason I was asking about collisions, because talking to your top neighbors is like a worst case scenario, right? And I know I can talk, because we have initial connectivity, I know I can talk to you and you can talk to Chris, and therefore once I can establish connectivity with Chris. But actually, Chris could be very close to Greg, he could be close to Sean, and we could all be moving. Right, but
if he's very close to Sean, then you could probably talk to Sean. If not, then he's further away from you. So as I move up, then yeah, that's right. So you can hear out 2-hop. You can hear.
Well, I thought it was 2 hops in the graph.
It worked for going one way, but what I wanted to do was go back.
Well, it's 2 hops in the graph, but you can talk. I mean, if you move.
To me if it's 2 hops in the graph, right?
Right.
Because he's not 2 hops in the graph, but he's still 4 hops in the graph.
Oh, yeah, that's no problem. But you won't collide with him unless he's with your neighbor. right?
Right, but like I said, the point is I can't just know about positions of people who are 2 hops within the connectivity graph. I
Right.
have to know more about.
You have to know your neighbors.
I see.
You have to know.
Physical space.
You have to know your your.
So there's a topological neighbor there.
There's a topological, right.
Right. Yeah. So again, I don't.
So when you said 2 hops.
I didn't review this part before I put this here because I just grabbed these slides from my colleague. I think you have connectivity constraints and then you have collision constraints that are built into this thing. So you're trying to force that I don't break my connectivity with the neighbor that I'm moving around, and then I also don't want to collide with any of my neighbors that I can physically.
Collision is collision, we're not packet collision.
Right. Yeah. Collision is physical vehicles.
And so for moving forward, so we're physical space and network space. What do we want to call it?
Well, we call it network topology and physical formation. So that we use topology and formation to distinguish between these two things in our work.
So in the network topology, I maintain, it's when I moved, that's about moving to 2 hop neighbors.
That's right.
The physical spaces, I actually have to know everybody who's within a physical radius.
That's right. I have to know you assume that we can communicate with everybody who's within my communication range, and those are the only people I have to worry about colliding with, right? It's fine, this is the point, and like I said, this talk is one that I put together for something else. This part of the talk I put together for something else, and so probably there's too much that was compressed out. So this is just something that one of the students that worked on this. So one student worked from the control student, one network student, and they kind of worked together and did all this work together. It turned out very well. Here's some arbitrary initial formation, some desired formation. The first step basically is label these guys in some way and then find the mapping. And so the number in parentheses is the position to which that node is mapped in this desired topology, right? So node number 1 here gets mapped to position 5. You can see node 5 here gets mapped to the center. He's at position 1, and so on. And so,
just a second.
Yep.
Real quick second. Okay. So this is network.
This is the physical formation. Physical formation. You can see they have position.
The links are?
The links are the communication links that exist based on the protocol model applied to this graph.
And when you went to the next one?
And when you go to the next one, then we reduce these things to trees, right? So this one, we just pick a tree. This one, we do subgraph matching and build a tree that has the mapping associated with it, right? So this is after we've done the subgraph matching and built our tree topology.
There's a dummy step missing, and I tripped over the dummy step.
Again, I'm just going too fast because I know this stuff. I've done this stuff too much, which is a problem. But you can see what happens, and so one of the things we wanted to show is so if I look at node 4, which gets mapped to position 2, he's supposed to communicate with this node that's mapped to position 7, right? In order to achieve this physical formation, he needs to establish a communication link here, but these two guys are too far to share a communication link. So when this nodes start to move, then what has to happen is that this node, if you look at what's going to happen, is that he is connected to node 1, but he shouldn't be really. So he's going to want to move up the tree. He's going to be assigned to move with this node that he needs to communicate with. They're going to share an information flow. But as he moves, you'll see he doesn't move towards here and then towards here. It's not like he moves in this way that these things are completely traveling along the network formation. He moves in a little bit more sophisticated way. And so let's see. I don't know if I can make it go. Should be a movie. Is it not?
I see a movie.
Should have said one.
It is a movie. Well, I can't even go to the next screen of my thing. I don't know what it's doing.
I think that whole thing. Yeah, up there you can gather windows on the left there if you want.
Let's try this again. Oh, there it goes. So these guys can already start achieving their physical formation. This guy is moving in such a way so that he can based on his information flow with him, and then they just keep going and driven towards their desired relative positions that goes in the navigation function.
Like energy function, it's
Yeah. So it's kind of like potential function type old stuff, but then they add navigation function. It has some other things in it, right?
So the navigation function is quasi-concave, which then increases, so it's quasi-convex. I mean, is there a unique minima to this?
Yeah, so navigation function, the controls guys prove that this, provided you don't start in some set of measure 0, that eventually it will converge to where you want, basically. That's it. It achieved the desired formation, so that's what the desired formation looks like in terms of the physical configuration. So there's this combination, this play between network topology and physical formation, and so we try to put all this stuff together. It's kind of an interesting problem, I think. But there's still a lot of stuff to do. In this work, one thing is that we are looking at the case of we want constant communication links. So we can't do anything with like fading or, where people block you or whatever. So we are doing a lot of work now looking at channels where the links drop and what should we do then.
Regimes, I mean, what are the actual applications? If it's radio and you're talking about quad rotators, you're not going to lose links.
Right.
So can you, since for the unclassified portion of the work, what?
Well, yeah, so we're interested in a lot of mixed.
How do you lose links?
Mixed.
Did you say you would not lose links if it's quad?
I mean,
Well, if it's
radio in a room
if
like
it's
this.
free space, but
Oh, okay. But who said it's small? Like
yeah, if you think urban environment, or caves where they want to send these things.
Around corners, whatever else.
Yeah, it's all.
So
and
you could imagine
the other problem that's big for them.
have you telling me truth movements.
Yeah, and Air Force in general, they are thinking mixed. Both you have air troops and ground troops, and those guys lose connectivity for all kinds of reasons. As the vehicles navigate, your antenna polarization or look angle changes, your dB gain on your antenna completely changes, and so the links go up and down for all kinds of reasons once you put ground vehicles into it.
Sort of question, the information exchange. What sort of information is being exchanged on those links? I'm just trying to get in the feel for overhead.
Yeah, so ongoing work on reducing control information. So yeah, they're exchanging a lot of positional information across those links to say, hey, now I'm here. How do I need to go to get to where you are? So my relative pose to you is this, and my position is here, and then they calculate their relative pose and compare it to what they want to achieve, and yeah, so a lot basically. So that's some of the things we're trying to address here. That there is still a lot of control, although we tried to keep the control as distributed as possible and not have like one guy in charge of moving the whole network around, which obviously makes it easier. There's still a lot of information that has to be exchanged.
Easier and fragile.
That's right. That's right.
is the only information that's exchanged control information, or do they also have, I don't know, they all have cameras and they exchange video?
Yeah, I mean, ideally, that's the ultimate goal, is that on this network, you'll be running some applications that you'll be pushing all kinds of information through there. And some of our work is that sometimes one of the things we look at is how can I optimize the formation to achieve some particular goals in terms of network characteristics. So I turn the problem around, so now I move the vehicles around because, hey, these guys need to exchange a lot of information right now. So, since planes, you have to fly them anyways, you might as well fly them around until they're close to each other, and then you can pump that information between them much quicker, right? So that's exactly right. So some other stuff like power control adds an interesting twist to this, because then, if I don't communicate with somebody, well, hey, maybe I turn on my transmit power and now I can communicate with them. I can take a shortcut through the physical space. So there's lots of interesting things that can be done here, I think. And we're just starting, so. Yeah, definitely.
So there are two situations. Situation one is so you allow control. There's no uncertainty. You have initial configuration. You have a final configuration. So you know where to move.
That's right.
You have central commander. Tell everybody you move to position 1. The second one position 2.
Yeah.
It's a simple case. Second case, we do it dynamically. Everybody move step by step. Eventually move to the desired position. Sometimes, especially with military network, you have some uncertainty. let's say there's no obstacle suddenly appear there, and the weather condition, you cannot move there because the thunderstorm. So how do you deal with this protocol?
Yeah, so I mean, the navigation function could be generalized to handle things like that would then allow you to be robust to some of those issues. But I mean, so for the first problem, it's still actually an interesting problem because we're considering this anonymous, what we call anonymous reconfiguration, where the vehicles are homogeneous and we don't care who goes to where. Some of the other work we did is actually figure out how to solve the graph matching problem in that case, where I'm interested in a physical formation, but I don't care who goes to where, and I don't care about the, where that is in space or the rotation of it. I just want to achieve a certain shape. Then that's also an interesting optimization problem that we've solved and worked on. The second case, yeah, that's some of those things that's interesting, especially when you start to introduce intermittent communication. So that now my communication links aren't as good as I think they are, and then how do I guarantee that the vehicles won't move so far that they won't reestablish communication, or do I move them closer together to make sure the communication link can close, or what do I do, right? So we're working on some of those things too. Yeah, here.
What's the attack aspect?
Yeah, so the attack aspect is this one. So I had two halves of the talk.
Okay.
Yeah.
Have you implemented this?
We've only implemented that in simulation. Right.
Plans of putting this on real
Well, quadcopters are pretty much out anymore because of the recent FAA stuff, although we are partnered with the Air Force, and even they kind of say that they're hoping to build like this Thunderdome sort of thing, like a big mesh dome that we can fly quadcopters in and out at Eglin, and then as soon as that, we plan to do things like that. Basically, we are going to be implementing some of this in a new project that's, I think, will start around summer, where we'll be doing both software-defined radio and mobile robots. But as far as what we'll actually implement here, it'll all be ground robots because of the complication of flying.
I guess underlying my question is, do the quadcopters, are there vehicles like this that have all the infrastructure you need, so you just need to implement the algorithm, or you need to actually still add hardware to it to be able to implement it?
Yeah, we could definitely implement this on the existing quadcopters. I don't think it would be a very big deal. What happened here? Just kicked me off. And we're interested in that. So we've been, asking the Air Force, and they kind of, at one point they're saying we have to do it, and the next they say, well, you can't do it. So we're somewhere in between. But so our solution path eventually is we're just going to buy turtle bots and run them around out in the parking lot when nobody's there, because it's better than nothing. And then the ultimate goal is at least to have, for our next project, is at least to have fixed wing aircraft and some ground stations and do some of the stuff we're talking about.
You have domed stadium around here, right?
We have a basketball arena, and I don't know what they'd let us use it, but that was a good possibility. Okay, so I did want to talk about the attack side. And so what I was interested on this, and this relates to the autonomous vehicles, is that I wanted to think about the susceptibilities that you have when now I have a system that's highly dependent on its communication to keep doing what you need it to do. So like a set of micro air vehicles or small air vehicles where I need control of them, then how would a jammer go about attacking such a network to disrupt its communications? And so what I was interested in is taking this idea that's been studied for many years about jamming communication links and thinking about instead jamming the whole network in some way. And so there's not much that's been done at this. And so let's just think about what happens if I want to place one jammer in my system. I won't consider all the places I could put it. But if I start over here and just kind of move through it, I could jam this node, but it basically does nothing for me except just reduces that one node, right? So this is sort of the old-fashioned jam-a-links sort of situation. It doesn't really affect the rest of the network at all. If I jam node 2, then at least I make 6 get orphaned from the network, and 2 is disconnected from the network, so it's a little bit better. If I jam node 1, then now I've taken even more, and there's just this remaining set of 4 nodes. But if I jam node 0, then I've partitioned this network into node 3 that's isolated, 2 and 6 are kind of isolated, and so I can think about how should I put this jammer to cause the maximum disruption.
you're going to specify the metric.
Of course, I need to come up with some metric of whatever I want to do, and I'll kind of give a couple. So yeah, partition network as much as possible, whatever that means. And I don't know, but we could think that we want to create more disconnected subgraphs, right? Because we don't want to allow you to have one subgraph that has a lot of stuff in it. And we don't, if whatever subgraphs we have, we don't want them to be large in some sense, because that set of nodes can still cooperate with each other. So I want to break the network up into small subgraphs. And so I kind of go through this in two quick takes on different approaches we took to looking at this problem. One is the case where I fix the number of jammers. So I have some number of jammers. We assume in our work that jammers block reception at nodes, basically. So jammers can have various different types of effects, but we'll say that if a node lies within some range of a jammer, then he's blocked from receiving. What we want to do is connect this to some sort of graph problem again. And so for a graph G, we want to find a vertex cut, so I'm blocking some nodes from receiving there, that maximizes something we call separation ratio. And if you look at what separation ratio is, then basically what is the size of the maximum connected subgraph, how many nodes are in the maximum connected subgraph that's left, divided by the order of the graph, and then I'm going to take 1 minus that just so it'll be an increasing function the more disruption you're causing, right?
So again, just to not hijack, but just get the clarity, there's just thinking into something that I can kind of understand, a military situation, have people looked at how to maximally damage this network is controlling some sort of real world function. So people looked at how to disable the real world function, which may or may not be related to the network. Not
really, no. Not that I'm aware of.
So you chose this kind of fragmentation metric, and that's kind of ad hoc.
Right. So this is of our interest because we're interested in control of this system. You want to make the system into pieces so that whatever pieces are left can achieve whatever the overall goal of the system is, right?
That's the thing that I'm questioning, and the intellectual connection between not achieving the goal and the graph separation.
Mm-hmm.
So I guess presumably study of ARPANET, for example. The original idea of ARPANET was exactly this kind of thing.
Yeah, provide some.
Maintain connectivity despite.
Right.
Right.
Yeah.
So
essential focal insults.
Yeah. So presumably there is some studies from.
There is some work on flow on if you have certain you're interested in certain pairs that have certain flows and things like that. There's things like that. But not just okay, I have some network, maybe I don't know what this the various objectives may be running across there, then how do I just disrupt that overall network? If there's something.
Maybe I want to disrupt fire control for the cruiser that's out bombarding the coast.
Right.
And I really don't care about the Marines that are on the ground. So
well, then
in that particular case, I just want to knock out the head end node, and I don't care about everything down below.
Right.
So that's I'm making it up just like you are.
Yeah.
I guess this is more the homogeneous
network.
Every node is equal to every other node. You're thinking more of a hierarchy of nodes. Some have different functions.
Might.
Well, I mean, if you have some subnetwork that's important, then you take the subnetwork and then you apply this to the subnetwork, right?
Well,
so
maybe, I guess what I'm getting at is that you already mentioned or raised the possibility that there are different sorts of platforms.
Yeah.
There may be an actual helicopter. There may be fire support. There may be artillery. There may be. I'm just using the military because that's easy and it's and it fits in with the attack.
Yeah. So this is sort of a starting point. Certainly
I'm not
we don't want to go too close to particular applications, because then whatever result becomes too specific to things. On the other hand, I would say that one thing I would like to go to is here we're just talking about breaking up the network, but maybe in a real network you have different types of overall flow through the network on different links, and maybe you want to break it up in such a way that information flow is minimized or something else. So there's lots of objective functions we can formulate, right? So have to start somewhere. Yeah.
Can I just ask for one last clarification? Can you tell me what order of the graph is relative to order? You just mean the total number of nodes, the whole graph?
Yeah, the cardinality of the subgraph, the largest subgraph that's remaining after I jam, divided by the cardinality of the graph that's remaining. So examples will help. So our decision was we decided that we're going to compute separation ratio. The denominator will be whatever the residual graph of the non-jam nodes is. And so when I just jam one node, then you don't get any improvement in the separation ratio. It's just a jam node. You know, the same as a link you have 6 nodes left in your graph they're not jammed. None of those are. You have 6 left in the largest subgraph, so that's a separation of 0. If I jam node 2, then I have 5 nodes that can still communicate out of the 6 non-jam nodes, and the separation ratio is 1 minus 5 6 is 1/6, and so this is 1/3. I have 4 nodes that can communicate out of 6, or if I'm down to 3 nodes that can communicate out of 6, then the separation ratio goes up to 1/2. Yeah.
Can I ask another question?
Yeah.
The model of your jammer, because here you're jamming nodes, and I usually think of a jammer when this is, you're jamming an area, right? So you're bringing links down. You're not necessarily going right next to a node.
That's right.
Right. Which would be one, and so you would have, again, if you had a different metric, which was not necessarily just disconnection, but just reducing, right?
But you need the geometry then. It doesn't have the geometry as a graph.
Right, yeah. So, this is a little bit of an abstraction, but jammers can cause a lot of different effects in practice other than just reducing signal-noise ratio. They can cause you to swamp your A to D. There's like a lot of different oddball effects that you see in practice that are not really captured by some of the physical. Yeah. So some of those things are, just abstracted in some sense.
It's really you're jamming a node.
That's right. So we think that if you are within some range, physical range of the jammer, you're jammed, basically. And so that's not, if it's just an SINR sort of thing, then that's not really valid, because if you put your communicating nodes close enough, then you can always get enough signal, right? But in practice, it doesn't necessarily work that way, because there's so many things that jammers do.
It could be a rocket launcher.
So, I mean, we will have a physical formation associated with this as well. That's going to, yes. So it's not just, I'm not just cutting up graphs in the end. Okay. So we'll get to that. But basically, if I just think about the problem, it's at least a combinatoric optimization problem. In fact, it's not necessarily even that, because we're going to think about physical formation, and then it's probably even worse. I'll show you an example. But basically, we kind of came up with 2 different approaches to this. One, we tried to come up with some semi-analytical approach based on graph cuts, and then the other is just use meta-heuristic search. And I won't say too much about these, but what we do in the graph cut is we use n-cut. We couldn't find something that's an exact match with our separation ratio formulation, but normalized cut is a commonly used metric for partitioning graphs, and it does relate in the right way to the volumes, inversely to the volumes, so that I'm trying to essentially make it so that this denominator will try to make it so that you don't have any large residual subgraphs left. But this cut has to do with the cut across edges, and I'm really interested in vertex separators and not edge separators. But there's not a great connection there between that, and so that's still work. But the good thing about it is that, I'm missing some parentheses here. The good thing about it is that, again, this formulation can be relaxed to a typical trace minimization using the graph Laplacian. This is the normalized Laplacian. This should be d minus a for the normal regular Laplacian. And so we can solve this fairly easily. But then what that gives you, it gives you edge cuts, and then from those edge cuts you have to build vertex or edge separators, build vertex separators, and then we do that by, and I'll show an example, by using a greedy approach because we're placing jammers in physical space to create the vertex separator from the edge separator. And then we do that in that way. So the advantage of this is it has reasonably low complexity, because the biggest thing is just doing the eigendecomposition here, and the rest of it's low complexity. The disadvantage is, first of all, when we do this jammer placement, we just look at placing them at the location of communication nodes. But that's not really optimal because I could place it between there and jam some other combinations. And right now there's some disconnect. We're using end cut for this purpose, but that's minimizing the edges cut or the weights on the edges cut, and we're really wanting to build vertex separators based on how many vertices, or not the number of edges, but the number of vertices that I need to cover. So there's a little bit of disconnect right now on that. Our other approach is basically using a harmony search for the meta heuristic, and so basically the idea of harmony search is you have some random set of jammer placements, and then you iterate over, you add some harmonies where you try some different combinations in and out, which are called improvisations, and then whichever one's good you find, you kind of keep those in your mix, and then you kind of improvise across them. And so it seemed a reasonably good match for this, and it works fairly well, in fact. So the advantage of this is that now our potential jammer locations can be anywhere in our radio field, and we can have some trade-off between complexity and performance by just change these parameters to the meta heuristic search. And the disadvantage is, well, we don't know how to choose the parameters for meta heuristic searches in general. You have to guess something and try it. And then it's also not clear when and if we can achieve better complexity than our other solution, or better complexity performance trade-off than our other solution. So here's just some example to show you how things kind of work. A graph, 100 nodes placed randomly, and then if we look at our doing the analytical solution, then just to create one cut through the graph, then this will be the edges. It says we should cut to maximally partition this guy according to the end cut criteria. And then from that, we need to build a vertex separator. And the vertex separator, basically, you try and find which vertices do I need to do such that I cover at least one vertex on each edge, right? I don't have to cover both of them, just one vertex associated with each edge, then I can disrupt all those edges. And then we start to place our jammers. Each time I just find which is the node where if I put my jammer, that I will cover the most of the vertices I need to block. And so we do that step by step. And so here we had 3 jammers. And when we're done, then the network gets partitioned such that separation ratio is 1/2, which means that half the nodes are in one of the subgraphs that's left over, basically.
So you do model the jammers just covering a certain area?
That's right. That's our model.
Wait, what was you just saying?
I think that was what I was asking before.
Okay.
Could you just restate the question?
Yeah, so exactly. She asked, is our model that the jammer just covers a certain area? Yeah.
So
and so we have
taking out one.
No, it's a physical, okay, yeah, there's a physical formation, and within that area we assume the communication is blocked by whatever mechanism.
That's also a bit weird because I would probably have overlapping circles, right?
Yeah, you wouldn't think that you would want to necessarily.
I could take that one and
But what you would probably want to do is, you see that this is the largest subgraph remaining, so you probably want to slide this one over, but we're using a greedy algorithm, so once this one's placed, we don't go back and ask again, right? So he was placed first in the greedy algorithm, and then when we got to it, we're like, oh, we need to put one here. And the other thing is we're limiting our placement of jammers to the communication nodes in this algorithm to simplify that part of it as well. So there's all these restrictions, and trying to get something going.
You know the adversary, so you're the jammer, and there's an adversary whose network you're trying to jam. There's a supposition that you know their network connectivity already.
That's right. We assume we know where everybody is. I mean, in some of our future work, we're trying to make it so that you find that out on the fly, right? Yeah.
And I thought your algorithm, I didn't know that it seems like it would be easy to modify your algorithm so it moves things around.
I mean,
it's memory, yeah.
We could generalize. It doesn't have to be greedy algorithm, right? So for this part of it, so this is what we did so far. Obviously, there's room for improvement here, and especially we could just tack on a meta heuristic search to this thing instead of just doing a greedy placement. And even with just a few iterations, we could improve this to something much better, probably.
Do the greedy thing repeatedly and pick the best one.
Yeah. So that's what we did to start, though. Comparatively, like here's what the harmony search does. So this is first iteration, just random placement. After 50 iterations, it still has a separation ratio that's worse than what we did with the analytical sort of solution. After 100 iterations, it's doing better though. After 800 iterations, it's up to 0.65. The optimal turns out to be 0.72, where optimal we just quantized all the space and tried every combination of choosing 3 places in space, right? So obviously that's not a, as the number of jammers goes up and the size of the space and all these things, you don't want to do that. So, but what we saw is that, and I'll show more results, the harmony search can get pretty close. What we've done so far, this is still far away and needs improvement, basically. And I can show you particular results on that as well. So this is some selected results. So here's separation ratio versus GS is our analytical greedy, that has the greedy search on it. HS is harmony search. And I wanted to show this particular combination because, so here's harmony search with 10 iterations. The analytical technique actually does better than that. So this is 5 jammers. Does a little bit better than harmony search with only 10 iterations, and the complexity of those two things is about the same. If I go up to 100 iterations, then basically I have an order of magnitude more complexity in my harmony search, but I get a pretty significant improvement in how much I'm disrupting the network. If I go up to 1,000 iterations, then again, I'm getting even better performance. And just as sort of a check and balance, like the black curve is a greedy search with 10 jammers, and you can see the more jammers, then yeah, I can certainly drive the separation ratio much higher. And the complexity for greedy search doesn't have to go a lot higher. So if you're complexity constrained and not jammer constrained, then go ahead and use a greedy search, because it doesn't cost you much there. But if you are device constrained and not complexity constrained in solving where you place them, then do the harmony search and find the thing that's closest to the optimal. And for smaller numbers of jammers, we've compared it to the optimal placement with this quantized sort of search, and harmony search is pretty close, basically. And so just to give you a second take on this thing, and this, I don't think this will take too long. Hopefully we can still have some discussion. One of the things is that, so this multi-way normalized cut is usually used in clustering algorithms, and a different way to solve the same problem, which has different objective, is to treat jammer placement as some optimal cluster assignment problem. And so the one we chose is to minimize the number of jammers required to partition a network into some specified number of clusters, where we put an upper bound on how big each of those clusters can be. So here I'm going to force your clusters to be constrained to some size, and then basically what comes out is some sort of binary integer program that looks like this. You wanted some math, right? So basically, J's are a number of jammers. We're going to minimize that. The x is xik is a 1 if node I belongs to cluster k and is 0 otherwise. And so every node has to belong to one cluster. Every cluster has to contain at least one node, and so I've put this in standard formulation. Clusters are constrained in size, so if I sum up the xiks over I, then I get the number of things within cluster k. I'm constraining that by some constant value. I don't want any cluster to get too big. Nodes close to a jammer will be jammed, and they're going to be assigned to cluster 0. So these are my jammers. If I am connected to the jammer, this Pij determines is the connection, physical connection, then I have to assign that node to cluster 0. Nodes that share an edge must belong to different clusters. Nodes that share an edge must belong to the same cluster. Is that right? What do I write here? Must belong to the same cluster unless one belongs to cluster 0. So I can't have any edges between clusters. I wrote that wrong. And the node at the jammer's location is jammed also, and at least one jammer is deployed, and everything's binary. So bad news is, of course, binary integer program is NP complete. So it doesn't necessarily help us to solve it this way unless we find some other way to actually solve the problem, right? So but this shows you something about the performance that, so if I want to get 2 clusters where I've constrained them to be about half the size of the total network, then I can get away with, when the network's small, it only takes me 1 jammer on average. When the network gets to be 100 nodes, it takes me around 2 jammers on average. The separation ratio is shown here. I'll compare that with some other things a little bit later. But you can see it's close to a half, which is probably, around the best I can do there. The performance then, yeah, so for reasonable sized clusters. So the average running time to do this with whatever CVX opt library takes about less than 100 seconds to cluster, determine the optimal jammer placement for 100 nodes when I break them into 2 clusters. But definitely going to be bad as time goes on, and I'll show that a little bit with some larger number of clusterings. Here, if I have more clusters, and again, I got my student to generate these, he's running these results last night, so these are pretty rough looking. 2, 3, 4 clusters, then the more clusters I want to create, the more jammers I need. But even if I want 4 clusters, then when the network's reasonably small, I can get away with 2 jammers basically. Just have to put them in the right places. And the separation ratio also generally goes up, but I'm not optimizing for that in this case. But the running time, is basically shows you that things are going to be bad. Even when I'm up to 30 node network, then I'm already at 100 seconds if I want to put 4 clusters. And so binary integer program is hard to solve basically. So we have to figure out what our next steps are there. And if I look at separation ratio, then I'm not doing as well here where I'm determining the number of clusters and minimizing the number of jammers versus here where I'm trying to optimize the separation ratio. I can be pretty far from the optimal in terms of that, but that wasn't my objective. And also the running time is bad for the binary integer program compared to even this optimal search placement for the jammers in separation ratio, because if you look at the number of variables, the way we created these indicator variables for clustering, there's a lot of variables. There's an excess of variables. So we're working on that formulation to see what we can do. But just give you some hints of things we're working. Of course, we assumed a lot of things, like we're interested in mobile networks. How do we now put them in mobile networks? So the network's changing. I have ambiguity about what the network is. Like, how do I capture all those things? The main reason I actually got into this is this last question. How do I adapt the system formation to make networks robust to jamming attacks? But to solve the blue team problem, I always solve the red team problem first, basically, right? Determine the optimal attack, and then determine how do I work backwards to say what should I do to prevent the optimal attack from disrupting me, because how else can I work? So that's why we got into this side of things.
Thank you.
Thanks.
No, the last one was my question.
Yeah.
So just to make sure I'm understanding this cluster formulation you had of the, so that with the upper bound on size, that's sort of saying I pre-specify how big every surviving chunk is allowed.
That's right.
And then we're trying to minimize the number of.
Yeah. It's very similar to work that was done on clustering for decomposing parallel processing jobs, where you want to break them up into certain sizes. They're going to go to these different clusters, computing clusters. So it's very similar to that work. Maybe done like. Oh, I'm sorry, I missed it because I saw your title. I was like, that sounds really interesting. and so I definitely will have to check out the video. But so it's very similar to that problem. It's just that I have these other ways that I actually have to create the clustering by doing the jamming that is not like that, right? Other question? Yeah, Oliver.
So it seems to be as a game problem. Say those attackers want to attack a network to bring down your performance. And as a designer, we want to have a topology which is robust against these kind of attacks.
Absolutely.
So different kind of a topology, we have different components. For example, we have a heavy tail distribution, still free network versus random ER network.
Right.
Network.
Yeah.
So do you have some insight on these kind of design?
I have no insight on that. I mean, I guess if you have like the small world network, then you have a lot of these long links that can help keep your graph more connected, essentially. That I suspect a small world network would be much more robust to these types of jamming attacks than just these random graph networks that we're building here, because those long links will solve some of your problems, right? But haven't looked at it yet. So yeah, that'd be fun.
People said this small world network is fragile but robust.
Yeah, exactly, right?
There is a literature not on these random network models, but on constructed networks. I mean, there is literature those kinds of, but again, there it's not, so the thing that would be different in your case is that when you're taking out a node, you're taking out all the nodes in the vicinity, right? So
Right,
which
yeah.
makes it-
A little more.
There's one just for taking out links, if you're taking out edges, I mean, that is a big literature.
Right, right. So our problem is just a little bit bigger. So maybe I should,
More familiar with it than I am, but it's pretty big.
yeah.
So I wonder if those,
I mean, it's probably relevant. Just have to see, you know, how we can build out from that. Just a little. All right. Well, thank you.